Hi, this is Kumar Singh from Design Analytics LLC, and you're watching another episode of Throwback Thursday. Well, the milestone research paper that we are going to review today in this episode of Throwback Thursday pertains to technology, or I wouldn't say just technology, a methodology leveraged widely in the world of AI, which is called few shots learning. And the origin of that is this research paper that you see here. Right? So let's try to understand. This research paper says one shot learning. We now have a variant that we call few shots learning, but the genesis of that is this research paper. So let's try to understand it. So in supervised learning, what we do basically is that we fit a model on a training data set and evaluate it on a test data set, right? That's the standard process. The training set typically contains a relatively large number of examples per class, right? So as an example, in a supervised learning context, the iris data set, if you are a data scientist, somewhere in your learning journey, you kind of use this data set to learn modeling, right? Hopefully, right? So in a supervised learning context, if you think about this data set, it has 50 examples per class and it's considered a tiny data set. For deep learning models, on the other hand, even a data set like MNIST that has 5,000 training examples per class is considered small. And this is the area that few shot learning helps address. It's a type of supervised learning for small training sets with a very small example to class ratio. And again, this was the research paper that proposed this approach, and it ended up becoming really important in the field of model development, machine learning, and AI. So again, if we revisit supervised learning, in regular supervised learning, we train models by iterating over a training set, right? Where the model always sees a fixed set of classes. Well, in few shot learning, we are working on a support set from which we create multiple training tasks. And then creating or leveraging these multiple training tasks, we assemble training episodes where each training task consists of different classes. So as you can assume, in few shot learning, the number of examples per class is much smaller. When specifying the few shot learning task, what we typically do, and now we are getting into I would say a really simplified aspect of the approach from the paper, right? So when specifying the few shot learning task, we typically use the term n-way k shot, where n stands for the number of classes and k stands for the number of examples per class. And the most common values are k equals to 1 or k equals to 5. That I have seen, right? So for instance, in a 5-way one-shot problem, there are 5 classes and each class has only one example each. So you can assume, right, with this, rather than fitting the model to the training data set, we can think of few shot learning as learning to learn. Right? So basically, in contrast to supervised learning, few shot learning uses not a training data set but a so-called support set. And from that support set, we can actually sample training tasks that mimic the use case scenarios during prediction. Now, with each training task comes a query image to be classified. So the model is basically trained on several training tasks from the support set, and this is called an episode. Next, during testing, the model receives a new task with classes different from those seen during the training. The classes encountered in training are also called base classes, and the support set during training is also called the base set. Remember, do not forget, the task is to classify the query images, right? So test tasks are similar to training tasks, except that none of the classes during testing overlap with those encountered during training. So that's kind of the gist of the approach That led to, as shared in this paper, that led to the few shot learning approach, widely adopted now, right? But why? Why is this paper important and why is the approach widely adopted? Let's go through some of the advantages. The first one, as you can imagine, data efficiency, right? It learns from very few labeled examples, unlike traditional deep learning models that need thousands or millions, right? It's specifically very useful in domains where data collection is expensive or scarce, right? For example, medical imaging, fraud detection, low resource languages. Rapid adoption. Well, it can very quickly adapt to new tasks or classes without retraining from scratch. So for example, a vision model trained with few shot learning can recognize a new object, say a novel tool in manufacturing, right, after seeing just a handful of samples. It has lower annotation costs, right? And all these kind of, you can see where they stem from. It reduces the need for large-scale human labeling, right, which is often very time-consuming, right, and costly. And it's very critical in areas like biomedical data or legal documents where expert annotation is both expensive and slow. It has better generalization. We touched upon that overfitting aspect, right? FSL encourages models to learn meta-knowledge, which is how to learn rather than overfitting to a single data set. It improves performance in open world settings where models encounter data distributions not seen during training. It's very useful in imbalanced and rare class scenarios, right? So many real world data sets, as we know, are imbalanced, right? FSL can learn to classify rare events effectively, which is vital in areas like cybersecurity, fraud detection, healthcare, right? Next, cross-domain transfer. Well, FSL methods like meta-learning or prototypical networks can transfer knowledges across domains. Example would be a speech recognition system, right? Trained on English and Spanish can adapt quickly to a low resource language like, say, an African language like Swahili. Computational efficiency, since only a few examples are needed, it's kind of common sense that it needs less compute and memory for fine-tuning, right? Yeah, so I think we can summarize it that few shot learning is valuable because it saves time, it saves data, it saves cost, right? And it also enables rapid adaptation, better generalization and personalization, specifically in low data or high risk domains.